So, in order to manage your car's maintenance schedule, it's imperative that you understand the principles of lubricant viscosity.
To use the outdoor grill correctly, we must calculate the BTUs emitted by each briquette, multiplied by the total number of briquettes, less the inverse square correction.
So then, you can understand how the heat pump passes bitter cold air over the evaporator coils, which are now at a minus 40 delta T, so it extracts warmth from the outside air.
Ah! Just what do we mean when we say we understand something? Most of the things we understand, we really have a common sense acquaintance with, not expert knowledge of. You might say you understand flashlights, and toasters, and charcoal briquettes, and light bulbs, and perfume, and almost everything else we encounter in everyday life. But try answering a few technical questions. How long will a new set of batteries last in a flashlight? Could you answer that? How about describe the spectrum of red and infrared heat waves that toast your bread in the morning? Is that a little tougher? What's the heat content in BTUs of a single charcoal briquette? Got you again, didn't I? Try this. How do you evaluate lumens, wattage, and average life data on light bulb packages when making a purchase comparison of different brands? Yeah, sure. We don't live our lives that way. We buy the batteries that are on sale, or maybe because they're staring us in the eye as we wait in the checkout line. We don't know anything about the toaster spectrum, but we do know exactly where to put the light-dark control to suit our taste. Evaluating light bulbs on the basis of lumens, wattage, and average life isn't too hard. We're careful not to exceed the maximum wattage for the intended light fixture because we don't want to give the smoke detector a real test. We don't know much about how smoke detectors really work either, other than we should replace the battery when needed and test them periodically. And the moral of all this is that a basic level of everyday common sense understanding serves us well. And it's that basic awareness of radiation safety that we're going to help you with in this video. So, radiation, what is it? Webster defines radiation as the process of emitting radiant energy in the form of waves and particles. The example closest at hand is right before your eyes. The electron gun in the TV monitor you're watching is spraying electron particles in a very precise way on the inner coating of the picture tube. The phosphors lining the inside of the TV screen receive this radiant energy of those particles and re-irradiate that energy as different wavelengths of light, or different colors as interpreted by your brain. The apple is red, the grapes are green, and the banana is yellow. And maybe you can tell me why so many yellow cabs are painted orange. The point is, right now, you're watching radiant energy, both particles and waves, in action. How about some other examples of radiant energy? It's the fireplace on a frosty night, the toaster warming your breakfast, or maybe your partner's warm feet that you maneuver your cold feet closer to, not touching, mind you, lest they move away, but just close enough to enjoy some of that radiant warmth or radiant energy. That's how we live our lives. So, some sources of radiant energy, like the toaster oven, could be hazardous, and we need to have some guidelines to avoid injury. Many other radiant energy sources we encounter in our everyday lives, like the TV you're watching now, or the remote control, or a flashlight, are not hazardous and therefore don't require any safety requirements. We let our children use them. What really bothers us is that our 8-year-old can take that TV remote stick and program the VCR, and we still have trouble setting the clock. But what type of radiant energy are we concerned with in a radiation safety program? Now here comes the non-technical technical part, and I'll make this as painless as possible. Everything is made of atoms. Each atom is like a miniature solar system with heavy particles in the central nucleus like the sun, and electrons in orbit like the planets. Now, here's the deal. Some kinds of radiation can disrupt the symmetry of that solar system atom by stripping away those electron planets. We call that type of radiation ionizing radiation, and the process of stripping away electrons ionization. And we should probably use the words ionizing radiation safety instead of just radiation safety, because it's this ionizing radiation that's unique. Our senses cannot detect it, yet biological damage and injury can occur as a result of it. So controlling this ionizing radiation is what radiation safety is all about. But before we discuss controlling the harmful effects of ionizing radiation, let's take a look around the home. There we'll find a number of potentially harmful and equally invisible particles and rays that can do biological damage or harm. Now, they are non-ionizing radiation. A simple electrical socket could be a source of potentially lethal particles if we're not careful. And even cutting the grass for the first time on a cool spring day could expose your skin to enough invisible infrared radiation to cause harm, a sunburn, a particularly tender sunburn if it's your bald spot. So, we're already accustomed to managing an informal radiation safety program in our own homes. Now that we have a little real-world perspective, let's gain some common sense understanding of ionizing radiation. There are really only two types of sources: machine sources and radioactive materials. We're all familiar with X-ray machines in the hospital or at the dentist's office. A chest X-ray can be very helpful to the doctor trying to diagnose a disease. Why do we call them X-rays? The answer's kind of interesting, actually. The X-rays that form these images we use today are the same as the X-rays that a German scientist named Wilhelm Conrad Röntgen discovered about 100 years ago when he sent these X-ray photographs of his wife's hand to the leading scientists in Europe. Not knowing what they were, Röntgen called these rays that could pass through solid objects and expose photographic film X-rays. He used X in the algebraic sense of something unknown. Just months after Röntgen's announcement, this X-ray of a hand hit by an accidental shotgun discharge was clearly a benefit to the patient. It guided the surgeon removing the shotgun pellets seen as black dots on the X-ray. Later, we were to learn that X-rays are ionizing radiation and could be both beneficial and potentially harmful. Beneficial to the patient being X-rayed, while potentially harmful to the operator if unnecessarily exposed while taking the X-rays on a continuing basis. That's why X-ray technologists stand behind a protective barrier before energizing the machine. The other source of ionizing radiation is radioactive material. After Röntgen announced his discovery of X-rays, a scientist in France, Madame Curie, isolated and identified radium and coined our word radioactive to describe radium's property of spontaneously and continuously emitting radiations. For years, radium was just about the only radioactive material available. It was used in medical applications for treating cancers, and it was popular to make things glow in the dark. A little bit of radium mixed in a paint could make anything glow in the dark, like dice, Ouija boards, dials, clock faces, or anything else. With a beginning like that, it's no wonder that the myth, radiation will make you glow in the dark, got started. Since the development of the nuclear reactor after World War II, the choices of man-made radioactive materials have mushroomed, pardon the pun. Today's choices and applications are virtually unlimited, and few of us realize how many industries use some form of radiation in the workplace. Radiation is used to inspect production line products, to look for defects in materials, and to measure soil moisture intensity at construction sites. It's used in steel mills, in drilling wells, and it's found in smoke detectors, ceramics, and a whole host of other manufactured products. The source of radiation that we should be most familiar with is the one we tend to overlook. It's the one that gives our entire population, all of us, our greatest total radiation exposure. It's not, or it's for sure. It's Mother Nature. We call it natural background radiation. At this juncture, we need to use a few numbers to give us some perspective. But let's use numbers we're familiar with. A year's worth of Mother Nature's natural background radiation gives us a radiation dose of about 300 millirem. So, what's a millirem? I'm not going to tell you. It's a complicated calculation for sure. And remember, I promised I wasn't going to do technical here. Let's leave it at this. A millirem is a common unit of radiation dose that we can use to describe the radiation exposure we receive. So, where does this background radiation come from? It comes from cosmic radiation bombarding our atmosphere, so the higher above sea level we live, the higher the cosmic component of background radiation. Taking a transcontinental airline flight will add a few millirem to the passenger's annual background radiation total, and frequent flyers get more. It also comes from the naturally occurring radioactive materials in the Earth itself, as well as from the materials we use to build our homes, offices, and buildings. The third source is in the air we breathe. We've all heard about radon, the radioactive gas that's everywhere. But before you get too worked up over all of this, remember, all these natural sources of ionizing radiation have been here since before dirt. Indeed, man evolved on this planet in spite of, or maybe because of, this natural background environment. We have lived with it for longer than recorded history, and the human condition evolved in an environment of natural background ionizing radiation. The second biggest contributor to our radiation exposure is from medical and dental x-rays, which average about 60 millirem per year. Wait a minute. What about nuclear power? Worldwide fallout from nuclear weapons testing, luminous clocks and watches, airport inspection stations, and all the images we typically associate with radiation. When we lump all of those together, they contribute only about 5 millirem per year and seem to get a lot more media attention than they probably deserve. Throughout this discussion of natural background radiation, remember that we're talking about the radiation exposure that the whole population of the U.S. receives. It does not include the occupational dose that our radiation workers receive. The bottom line is that each of us receives, on average, a radiation exposure of about 365 millirem per year, or about 1 millirem per day. Okay, now that we have a basic understanding of the nature of radiant energy, ionizing radiation, and natural background radiation, let's examine the two basic ways we can be exposed to ionizing radiation, external and internal. X-ray machines can give us external exposures. When we turn them on, they generate penetrating ionizing radiation. When we turn them off, they cease to be a radiation source. Moreover, after the X-ray is taken, neither the X-ray film, the patient, nor anything else the X-ray beam strikes becomes a radiation source. Radioactive materials also generate external penetrating radiations. Many industrial gauges emit gamma rays, which are virtually identical to X-rays. Gamma rays, however, come from radioactive materials, not machines. There are 3 protection techniques that we employ when working around these types of external radiation sources: time, distance, and shielding. We can use time to reduce our radiation exposure by keeping a close track on how long we're exposed to any external radiation source. How do we do that? Well, for radiation workers, how about if we reduce the number of days per week that you work? Say, maybe a 3-day work week. Yeah, but then your boss is going to want to reduce your salary accordingly, and we all know that won't work. A more practical way of using time to limit radiation exposure is to be thoroughly familiar with the step-by-step procedures for completing the job, have all the equipment we need readily available, and rehearse the procedure with non-radioactive materials, a dry run, if you will, before actually working with the radioactive material. The second protection method, distance, is a very powerful tool that we use regularly in our radiation safety programs to reduce exposures. And this all tracks pretty well with our common sense theme. The farther you are from the source, the less exposure you receive. So we try to keep everyone as far from radiation sources as possible, but some workers must be close to the source to perform the job. For those who are not involved in performing the job, the prime directive becomes, If you don't have anything to do, don't do it here. Maintain your distance. Now, be honest. This isn't hard to understand at all, is it? Hopefully it's not too boring either. Technical tends to be boring, and we're staying away from that. And that brings us to shielding, which we can think of like sunshine and clouds in the sky. Clouds shield us from sunshine. The thicker the clouds are, the less sunshine gets through. And the thicker the shielding is, the less radiation gets through. For those times when we can't get radiation workers far enough away from the source to get the job done, we use shielding to help protect them from unnecessary exposure. The classic shielding example is the X-ray machine in the hospital. When the film, patient, and X-ray tube are all positioned properly, the operator walks behind a protective shield before exposing the film. That's because a little exposure is a very small risk at best. Remember, the X-ray is a benefit to the patient, and the radiation dose the patient receives is part of our average 60 millirem per year. But the accumulated effect on the technologist from being exposed day after day, year after year, should be avoided. All right, now how about internal radiation? Radioactive materials can give both external and internal doses. If you're close to radioactive material, you could be irradiated by the penetrating particles and rays because the material gives off external radiation. If the radioactive material gets inside your body, you could be irradiated from within and receive an internal dose. And that brings us to another term we need to clarify: contamination. What's the difference between contamination and irradiation? Let's use one of our real-world examples. If someone puts on perfume or cologne, they have been contaminated by coming in direct contact with the material and are also constantly being irradiated by it. In addition, they are now capable of irradiating and contaminating others because they have been contaminated. That's really a terrible way to describe a $150 fragrance, isn't it? But you get the idea. If someone inadvertently gets radioactive material on them, they are contaminated and will continually be irradiated until the contaminant is removed. In addition, they now have the potential for contaminating others simply by touching them or touching something that other people come in contact with. So, contamination means actually having the material on you, while irradiation means being exposed to penetrating radiation being emitted by the radioactive materials. All right, how do we control contamination and the potential for unintentional ingestion or inhalation of radioactive materials, and thereby prevent cross-contamination? The answer is basically good housekeeping. In the laboratory, we make certain all workers wear protective clothing and gloves when they're handling radioactive materials. And when finished, they check the work area and themselves for contamination and wash their hands. Furthermore, everything that came in contact with the radioactive material, protective clothing, gloves, respirators, tools, rags, whatever, is controlled so it can be decontaminated before reuse or disposed of as radioactive waste. Finally, the workplace itself must be kept to the highest standards of cleanliness to avoid unintentional exposures. Again, simply good housekeeping. What we're concerned with here is the potential for workers to have traces of radioactive materials on their hands, for example, and then eat a sandwich, or just rub their face with a contaminated hand, because the radioactive material might get inside the body and irradiate from within, resulting in more serious internal radiation doses. That's why eating, drinking, smoking, chewing gum, applying cosmetics, and the like are prohibited in areas where radioactive materials are used. All right, I got a question for you. Why do so many people tend to fear radiation at any level of exposure? Just the word radiation seems scary. I think that fear was really born at the end of World War II when we suddenly learned that 2 cities had just been leveled by nuclear weapons. Concern over control of nuclear weapons and the potential for reactor accidents like Chernobyl continue to fuel that fear factor. And what I most hope I leave with you is some perspective between those kinds of events, massive radiation doses, and the potential radiation exposures that exist in the workplace. Let's start with what we know for sure about the effects of ionizing radiation. Very large doses, say 50,000 to 100,000 millirem received in a single exposure, is the level at which some people would begin to feel sick, nausea, vomiting, that kind of thing. Above 100,000 millirem, some people might die. And as dose increases, the radiation sickness becomes more severe, and fewer people would be expected to survive. At the level of 1 million millirem, we would expect no survivors. Now, how about the survivors of these very large doses of radiation? Our data indicate that they will have an increased probability of dying from a fatal cancer during their lifetimes. We're very confident about these numbers because we've followed closely thousands of individuals who survived the bombings of Hiroshima and Nagasaki. Let's look at the data of these survivors and keep in mind that this is a population that's been followed closely for over 40 years. Interesting, isn't it? Out of the 91,230 survivors, many of whom received very large doses, 6,270 died of cancer. Had those survivors not been exposed to radiation, we would have expected 6,039 to have died of cancer. Even with this continual scrutiny, we've only found 231 additional fatal cancers. And, interestingly enough, there were fewer increased cancer deaths in the survivors who received less than 5,000 millirem than we would have expected. So you ask, do occupational levels up to 5,000 millirem carry some long-term cancer risk? No one knows. There's no proof one way or the other. And here's an interesting statistic that you might not be familiar with. The probability that you, the average American, will die from some form of cancer is 20%. Put another way, 1 out of every 5 of us will die from some form of cancer. Now that's a little scary, but remember not to blame that statistic on radiation in the workplace. And that brings us to the crux of the matter. What would I be thinking if I were sitting in your chair? Just what are the relative risks of working around radiation sources? What can we document as the harmful effects of being exposed to low levels of radiation? The answer is, we have no evidence to prove that there are harmful effects associated with occupational exposures, and we have no evidence to prove that they are harmless. But because we know that high doses of radiation carry some additional risk of cancer, we assume that low levels may carry a risk of cancer to a lesser extent. And therefore, our radiation protection goal is to keep exposures as low as reasonably achievable. We have maximum occupational limits for radiation workers, those individuals who work directly with radiation sources. And we have limits for other non-radiation workers who may work in the same facility. The maximum annual dose is 5,000 millirem for radiation workers and 100 millirem for non-radiation workers. But we've established procedures that keep most workers' annual exposures much lower than these maximum limits. We control access to areas, post caution signs, label containers, require the use of protective clothing, along with respiratory protective equipment. We have special procedures for receiving and opening packages containing radioactive materials. And we require many workers to wear dosimeters so that we can document exactly how much occupational exposure they're receiving. And what does this documentation tell us? It tells us that only 1 worker in 1,000 receives an occupational dose in the range of 1,000 millirem or more. And here are the statistics you've been waiting for. The average annual exposure that the typical radiation worker receives is about 300 millirem, while the average non-radiation worker's additional exposure is nearly 0. But what does that really mean? Let's look at some relative risks that each of us faces just by being alive today, just to give us a frame of reference. Keep in mind that we have no documentation of any harmful long-term effects whatsoever at the occupational limits. But to be on the safe side, we assume that some risk exists right down to the lowest level of exposure. On that basis, the typical radiation worker who receives the average 300 millirem occupational dose this year might have an increased probability of dying from cancer of about 1/100th of 1%. In other words, if our worst case assumptions are correct, a radiation worker's lifetime probability of dying from cancer may increase from 20% that we all share to 20.01%. That 0.01% increase in the probability of dying from cancer is the same probability we all face of being murdered, or 4 times less than our chances of dying in an accidental death this year. Well, how about a common sense conclusion to all of this? The increased risk of developing some sort of health problem from working around radiation sources is, under our most stringent assumptions, very, very small indeed, and may represent no risk at all. So, if we continue to keep occupational exposures as low as reasonably achievable, we can continue to work with radiation sources and be safer than driving our car. And maybe that'll get you to buckle your seatbelt next time. Thanks for watching.